So welcome to this lecture. My name is Marisol Ripoll, and I work in the Forschungszentrum Jülich in the group of theoretical physics of living matter. And this lecture is part of an initial training on numerical methods for active matter. And the focus that I will give today is introduce you to one simulation method called multi-particle collision dynamics, which main aim is to introduce the possibility of reproducing systems with hydrodynamic interactions. These systems are frequent, especially in the microscale, and there are many of them, and in particular, systems of microscale active matter are particularly interesting, display particularly interesting hydrodynamic properties. So although you have had already an introduction in active matter, let me bring these three examples of microscale active systems, which are gold platinum colloids in a peroxide solution, which generate a concentration gradient around them, and that creates that they are self-propelling solution. Then we have E. coli bacteria, and you can see also how they move thanks to their flagella, and also inside the cell, the cytoplasmatic flow generates all these nice flows that allow the interchange of nutrients and other important functions of the cell. So besides things that are very different in this system, there are several points in common. And the one that I want to focus on now is that in all these systems, solvent is very profusely present. So solvent plays an important role in the behavior of these systems, which is not always clear. And if we want to investigate this system by performing computer simulations, the focus of today will be how to simulate this solvent. So the challenge is that the length scales involved in the system are very far away from each other. So if you think about typical colloids or that we have seen, or bacteria, they can be from 10 nanometers to a few micrometer scales, while the typical size of the solvent particles that induce this motion around the colloids, it's much smaller. It's something like 0.2 nanometers. So they can be 2 orders to 4 orders of magnitude separated, which is a challenge for any simulation method. And if you look at the relevant time scales in which the two scales involve, the distance can be much larger. It can be from 5 orders of magnitude to even 9 orders of magnitude. So we need a smart way of dealing with this problem, neglecting all the non-relevant functions of the solvent and taking only what is interesting for reproducing the fluid properties of the system. So the solution is to think about mesoscale solvents. And there has been many of these models developed in the last decades. Here you have a list of the ones I like that they are more relevant: Brownian dynamics, smooth particle hydrodynamics, direct simulation Monte Carlo, lattice gas automata that evolves into lattice Wolfman, and I think you will see it next week, dissipative particle dynamics, and finally the one that appeared last, but already 2 decades ago, it's called multi-particle collision dynamics. Some of these methods discretize the equation of the continuous, so are up-down methods, and some others are down-up, so they average properties, the coarse-grained properties of the microscale. By multi-particle collision dynamics is something which is born really in the mesoscale and lies there, as you will see soon. So it was in 1999 when Maleverens and Cabral proposed for the first time this method, already more than 20 years ago. And something that happened with this first paper is that so they proposed it from direct simulation Monte Carlo. You will see it's a variation of particles that propel or collide. Direct simulation Monte Carlo was doing by pairs. And what happened when they proposed this method is that they didn't give it a name. So they said it's an interesting mesoscopic solvent simulation, and since then people refer to it with different names. One of them, very extended, is stochastic rotation dynamics, SRT. Some other people at the very beginning have referred to it as real coded lattice gas, and then it was called MK from Malevance Capral, and something which is very commonly used now is MPCB or MPC. So always when you read about these all these methods, they all refer to the same system. And the main characteristics of the system is that it conserves mass, momentum, and energy, which makes that the hydrodynamic equations are completely included. And it also intrinsically, by construction, includes the effect of thermal fluctuations, as you will see soon. So what is the algorithm? The idea is that if you want to take into account the solvent, you take into account endpoint particles, and these endpoint particles can have continuous positions in space. They're distributed all over, not in a lattice, and they can have continuous velocity. So any direction and any modulo is in principle possible, and the dynamics takes place in 2 steps with a discrete increment of time that we are going to call H, the collision time. So in the stream step, the first of the 2 steps, particles evolve ballistically. They are not aware that there are any other particles. They just move happily, just with the initial position that they have for a certain amount of time, this H, and the velocity that they have been assigned. And after this stream step, they stop to do the collision. And in this collision, the particles are sorted into boxes, and they are going to interchange momentum with all the particles that are in the same collision box. In principle, if you would like to take this collision precisely, you will need to know where all the other particles are and what is the relative velocity to each of them. But what it's being done here is coarse-grain and simplify that interaction very much. So all particles are going to be aware where the others are just by the presence of, by what is the velocity of the center of mass. So you are a particle, you arrive to the box, and then you just know what is the velocity of the center of mass of that box, including which takes into account your own momentum. And then the idea is to rotate the relative velocity of the particle with the center of mass. So we have here, this is the velocity that before the collision. This is the velocity of the center of mass before the collision in that box that we have arrived to. And then the relative velocity to the center of mass is rotated by a random, by an angle alpha. And then the velocity of the center of mass is some bounds to it. And so you have here the initial velocity, and this is the final velocity. It is not a simple rotation, but it includes this effect of taking into account the velocity of the center of mass. So if you are a very fast particle and arrive to a collision box in which all the particles are very slow, you will become slower and give some momentum to all the particles in that cell. So the momentum is redistributed by the particles in the box. And this is here I write again the idea of the collision. And with this, you can see that although each individual particle is changing its momentum, if you consider the whole momentum in the box, so all the particles in the same box, after the collision and before the collision, you can see here very simple, but it's exactly the same. So each particle changes momentum, but in the box, within the box, momentum is conserved. And this is how it was proposed, but this collision has a bonus, which is that if you calculate what is the kinetic energy before and after the collision, it happens to be conserved as well. So we have that not only mass and momentum are conserved, but also energy. So with this simple collision, all in one, we have all the conservation rules that we aimed at the very beginning. And what is it, this random rotation? So in principle, we have a fixed angle that the particles are rotating, but the idea is that, for example, in 2 dimensions, you choose a plus or minus angle alpha. So within each, if you are in a collision box, then you just rotate with the collision matrix. And if you are in one collision box, all of them rotate with the same angles, but in different collision boxes, it's each time chosen randomly if it's plus or minus. So in different instants of time, you can rotate plus or minus, and your neighboring boxes can have whatever rotation with equal probability plus or minus. And this is enough to include thermal fluctuations. In 3 dimensions is a little bit more complicated. The first option that was first easy option that was introduced was to choose not only plus or minus, but plus or minus in each of the axes. So instead of 2 options, now we have 6, and then the rotation matrix can be trivially written. But there is another more interesting option, which is to choose in each box a random direction. So you need just 2 random numbers to choose this direction, and around that direction in that box, the rotation is performed for all the particles. So this is very interesting because it's much less anisotropy. So the effect of the lattice is much more forgotten, it's less taken into account, and it's the one that it's mostly used when you are doing 3D MPC simulations. And well, a test that many of these systems have to take into account is if they fulfill Galilean invariance. So Galilean invariance, as you know, is that a system which is at rest and a system which is moving at a certain constant velocity have to be exactly the same. This is what you need by Galilean invariance. But here you see that I've highlighted 2 particles in red, and then the environment that you have in the system at rest and the environment that you have in the system with moving is not exactly the same. So here is a little bit naive, but if you do that with a system that is moving fast and you look at the diffusion properties in the 2 directions, it can be seen that there is a difference. And this means that as it's here the system, it doesn't fulfill Galilean invariance. So this is something that was realized in a very early stage of the method by Thomas Ilya and Dan Kroll, and they identified the problem and they already proposed a solution. And the solution was to say, why do we need to have the random box always starting at 0, always starting with my box? That's in a way arbitrary, and you can start it a little bit different in each collision. So you can start whether with a box like the black grid or the red grid, or you can change it to any other grid in every time step. This random shift implies that Galilean invariance is now restored, because the environment of the red of each particle, it is not going to depend if it's moving or not, because it's always going to be randomized in the effect in the surrounding, and it will also help to to delete any effect of these collision lattice that we have. And it has more consequences. One of them is that the interactions are smooth over distances, namely, each particle has a probability of interacting with a particle close to it, which is inversely proportional to the distance. So if 2 particles are very close, it's very likely that they will interact, and not that the grid will be exactly between them. So it's proportional to their distance. And another consequence that random shift has is that the interchange of momentum for collisions, so if 2 particles interact in this collision box at the very beginning, and the box displaces, the momentum will be displaced much farther and much quicker, which is a property that liquids have and that we like it especially. So collision transfer is enhanced as well. And well, this is the main ingredients of the method. And you might say it's a little bit naive to think that it's nice all, but why does this reproduce the properties of fluids? There has been a lot of work since it was proposed in 1999 by different groups. And well, so far, so good, is quite consistent that, that the method works very nicely. So it has been checked that we have conserved quantities in phase and space volume, that if you are in equilibrium conditions, the system goes very nicely to the Maxwell-Boltzmann distribution as it should, and other equilibrium properties are also fulfilled. You have, for example, you have an H theorem, and it can be checked that the hydrodynamic equations of for the fluids, Navier-Stokes namely, are reproduced by this system. You can calculate the transport properties as a function of the system parameters that we will see right now. And if we apply this method to different systems and compare the hydrodynamics flows that it's generated by this MPC solvent with the ones that are generated in the simulations, So far, we have got a beautiful agreement. So the point is that many times we know how this solution has to be, such that this is just a test, but in the cases that we don't know how the hydrodynamic solution looks, we trust that it also has to be the hydrodynamic behavior. So it's useful. And now I want to say something about the units, which are the main units and the main parameters in MPC. And in principle, I've already said it so far. So one of the main length scales in the system is the size of this collision box. You can have a collision box A that can be twice as large or a half of this, but we choose it typically as 1 because it's one. We say that this is the simulation unit of length. The mass that each of the particles has is the unit of mass, and then we need a third quantity that will give the scale of time or of energy, and it's typically chosen to be the system, the temperature of the system. So these are the most common units chosen for an MPC system, and out of these you can construct the time units or anything else, or velocity or anything else that you might need in the system. So in terms of the collision box, the particle mass, and the system temperature. And which other parameters are important in a simulation? We have to think about this streaming and this collision step. In the streaming, we have seen that it occurs during a certain time h. So this collision time is going to be crucial, because you can think that the displacement and the characteristics of the system, if you have a displacement, a very small collision time will allow a very small displacement of the particles, while if it's very large, it will displace for a much longer time. And this is, so the collision time is related to the mean free path of the particles, and it will be an important characteristics. Then we have the rotation angle. So if the particles are interchanging momentum through this rotation, it will not be the same that this angle is very small. It would be a very that it would be much larger. And a third quantity that is relevant is what is the number density, namely on average how many particles are in each collision box. It can be 1, 2, 20, 50. So the properties of the solvent that you have are going to be related with this number of particles per box. There is an additional quantity, which is the system size, how large, how many collisions we have, but this one is typically related to study the finite size effects of the system, which is very important, but I would not say it will characterize the fluid. So the main system parameters that we are going to focus on are these 3: the collision time, the rotation time, the collision time, the rotation angle, and the number density. Good. So now I will tell you just about one of the transfer properties of them having studied, which is the viscosity. You can study analytically by thinking how momentum is transferred in the streaming step and in the collision step. You can calculate through kinetic theory how is the transfer of momentum. And we have 2 contributions for this transfer, which give rise to the kinetic viscosity and to the collision viscosity. So the kinetic viscosity speaks about, you have here in green, and it's the amount of momentum that is being transferred by a particle, because the particle is moving from one place to another one. So I have a certain amount of momentum, and that comes with me to where I am. So this transfer of momentum is going to be increased with the collision time. So the farther I move, the more momentum is transferred. And then the other transfer is very interesting, is the collisional transfer of momentum, which is the momentum that I transfer because I gave it to the other particles in the collision box. So you know this famous example of the balls clicking to each other, and this is collisional transfer that also happens in random shift. And this one, as you might understand, happens much more if the collision time is smaller. So it increases with the inverse of the collision time. And these expressions, the total viscosity will be the sum of the 2. And you see here how the viscosity changes with alpha and with the collision time. And what is very nice in this method is that in spite of the approximations that have to be made to calculate this transport of momentum, the result of the simulations agree very well with the analytical expression. And And something else that I like to say is a dimensionless number, a number that, because these numbers are all given in MPC units, and the dimensionless numbers we can compare to any real fluid or other methods. So the Smith number is the ratio between the kinematic viscosity and the diffusion coefficient, the mass diffusion coefficient. So it's a ratio between the momentum transport and the mass transport. And we know that in gases it's of the order of 1, because gases move very far away without colliding with others, while liquids have a much larger importance of the momentum transfer, and they have these two things well separated. Water, for example, is of the order of 500. So in liquids, we know that it's from 100 to 1000 order of magnitude. So how it is with MPC, it depends on the parameters that you are using. It depends on the alpha, it depends on the A, on the collision time, and it will depend also on the density. And here I've put the analytical results, and you see that we have here an area for large values of the collision time that is constant, that it doesn't vary anymore, and that it's very small, so that it behaves a little bit like a gas, like you have here for the gases. While if you go to small collision times, if this time between the collisions is not too large, you can get really high values of the Smith number, and you can have this liquid-like behavior, especially if you don't use very small values of alpha. If you have reasonably large values of alpha, then you can get to large values of the Smith number. So this is what we have called collective and particle regime. And of course, if we want to reproduce hydrodynamic properties of colloids or of bacteria, we will work in this regime of large values of alpha and small values of H. And something else, if you want to study systems outside equilibrium, the point is that you will be able to use most of the strategies that have already been developed for previous methods, like molecular dynamics or grounding dynamics. So for example, if you want to study a system like capillary flow, you will have interactions with the wall and the effect of a force parallel to the walls, like gravity. If you want to study shear flow, we can impose Leeds-Edwards boundary conditions, or if we want to study, that I like especially, a temperature gradient, it will be enough to thermalize the temperature at the two walls. Here, the energy is not conserved because you are including, it might not be conserved because you are pumping energy by including this force or by including the shear flows, or if you have any beating pattern. So it might be that thermostats are necessary. It happens quite frequent, in fact, but it's due to the additional things that you are doing to the system to put it outside it. And with this, I would like to give detail in one of these systems, especially because it's the one that you will see on the exercise. So it's the implementation of a capillary flow. And the idea is that you need to implement the boundary first, the walls. The walls are implemented the same as in molecular dynamics with the bounce back rule. The bounce back rule says that if you have a particle that it's going in the wall, you will reverse the path that it comes from, and you will reverse the velocity, such that on average the velocity is zero at the wall. So this is the so-called stick boundary conditions. The velocity is on average zero close to the wall. But in MPC, you have to take into account that when you are close to the wall, we have the random shift, and the random shift makes that there are some boxes close to the wall which will be partially filled. And here there might be an effect that doesn't feel like in bulk. And in fact, what happens is that the bounce back doesn't work so perfect. It induces certain sleep. So what has been done is to include the effect of big particles, which means since you are seeing the effect of the collisions only through the velocity of the center of mass, you can say to the velocity of the center of mass, okay, if you are at the wall, and this box has been partially filled, you have that there is an additional contribution from some particles that are probably at the wall, and these particles are going to have an average velocity zero, which is what I want to obtain at the wall, and an average temperature the same as in the bulk, and the density that you would also, that I need to compensate and have the same density as in the bulk. And this gives already a quite reasonable agreement with having the velocity at the wall zero. And now I want to say that for this problem of the capillary flow, we know that the Stokes equations reduces the Navier-Stokes equation reduced to Stokes because we are in the small velocity regime, and this gives as a solution a parabolic profile. So what we expect in this parabolic profile, but this nice parabolic profile that we get here, the point is that analytically, it can be checked that this maximum velocity that you get here is going to be determined by the width of the channel, by the force input that you put, by the density of the system, and by the viscosity of the solid. So in principle, we just have our collisions with our alpha, with our rotation, with our collision time, but we are not saying explicitly to the system which viscosity it should have. But the system has a certain, so evolves with the collisions, and will develop a profile that will allow us to measure the viscosity of the system. So we don't have it as an input parameter, but we get as a result this velocity. And that's the one I have shown in two transparencies before that had such a good agreement with the analytical calculations of the coming from kinetics. So this you will see further in the exercise. And then I continue telling you until now everything is beautiful about MPC, but it has of course some pitfalls or some things that have to be taken into account a little bit more carefully. And one of them is the equation of state, which is the equation of state of a fluid represented by the MPC method. So we have seen that in the streaming and the collision step, there are no potential interactions at all. And this means that the equation of state that the system is going to have is that one of an ideal gas, because we need potential interactions in order to have something that deviates the gas equation. So what we have is a liquid with the ideal equation of state. What are the consequences of this? So the first consequence is that if your system is a binary fluid or a systems in which phase transitions come out of a non-ideal gas equation of state, you will need to make the method a little bit more complicated. You need to put something else into MPC to have a different equation of state. And the other consequence is that if you have a system in which the temperature is not homogeneous, in which the temperature varies, the density is also going to vary. Here I show you an example of a system with a temperature gradient, and you see that the cold and the warm are also related with a dense and less dense density. Is this going to be important when using the system for simulating temperature gradients? Is always a question that has to be kept in the back of your mind. But I can tell you that so far, all the things that we have tested, it looks like it doesn't have an effect. And here, I show you an example in which a colloid is moving in the presence of a temperature gradient, actually due to the presence of the temperature gradient. And this system can be again solved analytically. So this is what it's expected that the system would do, and this is what we obtain by the simulations. And you see that qualitatively is very similar. And if you look quantitatively, these two curves is also very similar. So although there has to be only very close to the colloid is a little different. So although you have to keep an eye in compressibility effects, we see that the effects are not really very large, and it's very nice. So the method is still very nicely reproducing the properties of liquid with temperature gradients. Let me say that there are already ways of making the system more complicated in order to include the effect of a non-ideal gas equation of state. One of the papers is from 40 years ago, and the other one is much more recent in the group of units as well. And besides these variations, I want to summarize now. We have seen this stochastic rotation in which we have the rotation of the relative velocity to the center of mass with a fixed angle alpha. But you could say, why has this angle have to be fixed? It could change from collision angle to collision from box to box. And the answer is yes, it could be, and this is called the MPC random angle method. But then you lose this dependence of the viscosity. So it will, and actually it's almost not used, this method, as far as I know. And for the systems in which the thermostats are very heavily used, this other method, you say, why do I need to rotate the relative velocity of the center of mass? I only need to keep the velocity of the center of mass constant. And then the other things can be interchanged in a different way. And here what they have done is to say, we have the velocity of the center of mass, velocity which is chosen randomly from a Maxwell-Boltzmann distribution, and then we keep back the sum of these randomly chosen velocities in order to ensure the conservation of momentum. And this is the so-called MPC Anderson thermostat method. I've not told you so far that another of the problems is that, as it's defined here, angular momentum, so linear momentum and energy are conserved, but angular momentum in the cell before and after the collision is not exactly the same. These, if you have systems in which vorticity is very important, might be a problem, such that there has been already methods that propose that you have to include a term in order to correct for these change in angular momentum. And here you have the option for the MPC with Anderson thermostat. And well, the methods with non-ideal liquids I've already mentioned. So there is plenty of literature to revise if you are interested. But let me continue and telling you how to implement complex structures. So until now, we have been studying just the solvent. A solvent like water. Water is the solvent of life, and it might be even warm water, but if you want to study something with a little bit of fundament, like lunchtime, it is just water. So if you want something with a little bit more substance, we need to think about something else. What have we to do for MPC in order to be able to have complex structures? So what it's done typically is to hybridize the model. So we hybridize, we use multi-particle collision dynamics together with other models. And for this, you have to consider that there are always three interactions to take into account. One is the solvent with the solvent, which we will take MPC, because if not, it would be another lecture. Or and then you have to see what do you want to simulate. Do you want to simulate colloids, polymers, membranes, what? And for that, you need a specific model that reproduce that system that you want. So it will be molecular dynamics, triangulated faces, surfaces, or whatever is your favorite system. And then the question is, how does the solute seize the solvent? How is going to be interchanged between the solvent and the solute, which is crucial, of course. And there are different answers. I will mention briefly MPC coupling, NV coupling, boundary conditions, and there are other couplings. There are other couplings that are still being developed. Maybe you come with a new suggestion, but I will not speak about it. Good. So the simplest way of interchanging information between the solvent and the solute is also using MPC. So we have MPC, solvent, solid, solid, and here we say the solute particles are just one additional MPC particle. So since we are considering both molecular dynamics and MPC, you have to take into account that we have here two time scales, the time integration of molecular dynamics and the collision time coming from the MPC collisions. And typically the integration time is much smaller depending on the potentials that you are using. So you have many MD integration times, and after 10, 100, whatever you need, you stop the MD dynamics, and then there is the interaction with the solvent. This is how it's typically arranged. And in the MD time, you will have to consider in this case only the solvent, because MD only affects the solvent. And with MPC, you would have to stream the solvent on the one hand, and then consider the interactions between the solvent and the solvent. And as I said, this is just an MPC with the same collision rule that we have, but here the velocity of the center of mass has to consider the solvent particles plus the solute. The solute typically have larger mass, which enhances also these interchange hydrodynamic interactions between them, but it's just one particle in the velocity of the center of mass. So there is no difference between solvent and solute. And of course, what is curious is that there is nothing that excludes the position of the solvents to be inside the solute. So if you have colloids, it's just penetrating freely through the colloid. So we have done all this way to simulate the solvent and the solute, but here the solvent is treated as a point particle. So it's a point particle, it doesn't take space, and is this approximation good? Is this a valid way of using these interactions? And I hope I convince you that yes. And this is with a very well-known problem, which is to study the dynamics of a polymer in equilibrium. So how to simulate a polymer is you just have your favorite molecular dynamics code for a polymer, in which, for example, you have harmonic springs that link together the different bits of your polymer, and you have excluded volume interactions between them in order to avoid that they interpenetrate. But this is only for the color. And then we have the MPC interaction with the solvent. So if we study the polymer center of mass diffusion coefficient as a function of the length of the polymer, of how long this polymer is, it is well known by theory that if you don't include hydrodynamics with this Gaussian chains model, with the Gauss model, what you expect is that the diffusion coefficient decreases with the inverse of the square of the radius of gyration. But if you do experiments with systems at different lengths, or you do same dynamics, which takes into account the effect of hydrodynamic interactions, it has been seen, it's known that the diffusion coefficient should decrease with the radius of with the inverse of the radius of gyration. So all of these we don't say to our MPC solvent. We just have the molecular dynamics together with our MPC collision with our point-like particles and everything. And what it's obtained is that it decreases beautifully, perfect with this radius -1. So it decreases with the inverse of the radius of gyration, which means that hydrodynamics, that polymer dynamics includes very nicely hydrodynamics. There are other tests, but this is the one I like to show in a simple manner. So in this example of the polymer, we have a very clear way of comparing what happens with and without hydrodynamic simulations. But since we aim at using this system out of equilibrium, we don't know what's going to be the effect of the hydrodynamic interaction. So in this case, it's very nice to have a method in which you say, I'm going to do twice the simulation, once with hydrodynamic interactions and once without. And random MPC, this MPC coupling allows very nicely to compare with this method, which is called random MPC, because here the idea is that the polymer is seeing the effect of the solvent only through the velocity, only with the particles that are in the same collision box. So it's not really aware what happens and how the information is transferred over the rest of the solvent. It's only with the interaction in each of these collision boxes. So what happens if we change, since we don't want to have any of the correlations brought by the collisions, we just want to have the effect of a solvent, we say instead of having all the solvent particles, we couple it to a bath. We couple each particle to a bath, and we treat this bath as if it would be MPC. So we have the velocity, we can calculate the velocity of the center of mass, similar as we have seen with the virtual particles and the walls, by picking up Maxwell-Boltzmann distributed number with the same density, temperature, and average velocity as the bulk, and we just put it here and we perform the same MPC simulation. So with these we have a beautiful way, so the system is exactly the same with and without hydrodynamics. It allows a very parallel comparisons. And you have the same 2 time steps, and all these effects are exactly the same with and without hydrodynamics. In principle, you could use also Brownian dynamics, but then you never know if the viscosity is the same or if whatever difference is related to the different methods or to the presence of hydrodynamics. So, and now I want to show you an example of this, of an application of MPC with an MPC coupling with these point-like particles to reproduce the properties of an active system of bacterial motion in particular. So first I show you these nice simulations of flagella, in which they have a polymer-like flagella that they have imposed not only harmonic interactions, but also this helicoidal shape, and they are linked to a wall, and these particles in the wall are moving, so this motion is imposed. It's supposed that they are rotating at a certain frequency. And the interesting thing is to see how these flagella are interacting with each other due to this motion and due to the presence of the solvent. And here you see that they could repel each other, that they would be crashing against each other, but what they like to do is this bundling together. This is a very nice work that has also been made a little bit more sophisticated to really reproduce the properties of something more bacteria-like by having the body of the bacteria and by complexifying a little bit more the model of the flagella. And you can see you can have bacteria with one flagella or with many of them, and you can study what is the flow field that one of these bacteria is generating. So you are not imposing, but you have here this very nice pusher type of motion that it's induced by the system, is induced by the motion of this body with the flagella due to the interactions with the MPC solvent. And this movie is a little bit similar here, you are going to see, but I find this beautiful movie of my colleagues in Jülich, in which you see how the flagella very nicely bundle around the motion of the bacteria. And okay, so these point-like particles, this solvent point-like was quite acceptable in the end for these systems that we have looked at, but you can think that it will not always be it will always not always be ideal, such that for depending on the problem, all other couplings have been developed. And if you need interactions different, so if you need that the solute has a spewed volume with the solvent, the first approach, and a quite valid one, is just to use molecular dynamics, is to say, I don't let the solvent penetrate into the solvent and I solve that interaction by simple molecular dynamics. So here we have again the 2 time steps, and the time integration of the molecular dynamics and the collision time. And in one case, here you also have to take into account the solvent, which is close to the solute, and by the MPC, only solvent-solvent collisions are accounted for. And the nice extra that this has is that you can change the interaction between the solvent and the solute. Namely, you can have solvophobic and solvophilic interactions. You can say my solute, and this is very physical, this is in many systems an important interaction that you can change. You can make it long range, short range, steep, everything is possible. Our first application of this was to study indeed the solvent quality for polymer dynamics that was being changed, and you could see very nicely how the polymer was collapsing when changing from a solvophilic to a solvophobic conditions. And in terms of active matter, a very important example that this has been used to is to simulate active phoresis. I don't know if active phoresis has been already introduced in the school. So just let me briefly say that if you have a colloid in a system that it's not homogeneous, doesn't have homogeneous properties, it can be a gradient of temperature, warm and cold. It could be that you have different concentrations of reactant and solutions. It could be that you have different ionic concentrations also. So then you would what happens is that the interactions are different in the surface of the colloid, and that results in the drift of the colloid. This is called phoresis, the phoretic drift, and it can be up the gradient or down the gradient. And depending on the origin of the gradient, it's called thermophoresis, electrophoresis, or diffuser phoresis. So if you want to simulate this with MPC, you need to have these interactions of the solvent in the surface of the colloid. And that's because that's what it's going to bring you the phoretic effect. And well, this is the problem that I've been working in the last years. So I show you here just one example for today, which is a Janus particle, in which that has 2 beads. One of the beads is hot, is kept at a stronger temperature. So it simulates the idea of that the particle is gold, for example, and illuminated such that it gets warmer in a colder environment. And then the other particle with this is attached will respond phoretically. In this case, it goes to the gold side, so it will move against this heat bead. And here you can see the hydrodynamic flow field that it's imposed. So it's a little bit polar type again, but it's absolutely not force dipole type of interaction. It's much more, it's distorted in a very interesting way. And that's a result of the interactions of the surface with the hydrodynamic solvent for this problem. So with these all these boundary conditions, we can reproduce properties, and with a parallel code, of course, we can study what happens when you have many of these colloids together, and since they are have also repulsive interactions because they don't like the heat, they form these clusters that they dissolve very quickly. But these clusters are ordered due to the presence of these interesting hydrodynamic interactions in very aligned, and they swarm together for some time. So this I will explain you more in another moment. And now I like to change to the last option for the coupling, which is not MPCA coupling, not MD coupling, but a coupling in the boundary condition. So you say, why not to treat the boundary of whatever you have, whatever colloid or surface, as if it would be a wall. And that was a very first approach for it, to say, okay, if you just treat it with appropriate bounce back, or you modify it smartly, that might give also a proper coupling. And this was a very first example done with treating the colloid as an obstacle, and you see the formation of this nice high Reynolds number type of flow. And if you, but this has also been used to simulate active matter with squirmers in which the velocity around the colloid it's very particular. So here you know that the squirmer velocity has a slip around that depends on the angle. So it's propelling in a certain direction, and depending on the angle, the flow slips more or less. And following this expression, you can change not only the propulsion velocity of the flow of this swimmer, which can be faster or slower, but also the hydrodynamic character. So if you have here the beta is 0, you will have a swimmer with neutral hydrodynamic interactions. If it's negative, it will be a pusher, and if it's positive, it will be a puller. Besides the surface velocity slip, in order to have proper, the same as it was happening with the flow field, you need the presence of virtual particles to have more adequate the velocity slip that you want. And furthermore, if you want to let this system to move, you will have to take into account the rigid body dynamics of the colloids. So there is quite some literature about this. That I just chose this very recent and nice example that shows two spherical colloids which are strong pushers very close to each other, and you see these very involved hydrodynamic profile are completely not trivial. And here I also like to show you a movie for a system of these elongated squirmers, which are neutral in this case. So here you can investigate what is the dynamics of all these clusters that are being formed. And with this, I'm at the end of my talk for today. I hope I've convinced you that, in spite of its simplicity, multi-particle collision dynamics is a very interesting model that allows, as I said in the title, to unravel the hydrodynamic properties of many systems, in particular active matter, which hydrodynamics are in many cases very, very important. So I've shown you a few examples, like simulations of bacteria, of red colloids, and of squirmers. And with this, I would just like to thank you. I would like to thank all the people that have helped me during this year, many students, and in particular, I want to mention today to Roland Winkler and Gerhard Bomper in the group of Jülich, who introduced me to the method and who have both done a very big work in making this MPC, this multi-particle collision dynamics, much more solid, interesting, and able to apply to different systems. So I also want to acknowledge different sources of funding. and computational resources, which for these simulations are, of course, very, very important. And with this, now I would like to thank you for your attention. And I would like to tell you that I'm available the day 20th of January for questions. I hope we have a very lively discussion. And afterwards, if you see this talk as well, this is my email. You can contact me for questions about multi-particle collision dynamics that I always find very interesting. So thank you very much. And we see another day.